one important thing that I hope you will learn in today's lecture, and this is probably the major part of today's lecture, is that we will learn that the mechanical resistance of a crystal is directly related to the ease of generating and moving dislocations. In other words, what that means is that the mechanical properties of a material strongly depend on how easy it is to produce dislocation in these materials. So if I apply a stress into a material, how easy the dislocation formation will be. And also, once you do have dislocations in the material, how easily do they propagate throughout the material, right? So if I have this defect here, again, if I continue to apply a stress, this dislocation will move throughout the crystal until you reach the plastic deformation, right? So this is what we learned last time. So how easily these dislocations will be introduced in the material and how easily they propagate throughout the material will determine the mechanical properties of the materials. So there are two important consequences of that. So first of all, we will learn that this is the reason why certain materials are brittle and some of them are not, right? Why can you deform metals, but you cannot deform ceramic materials? If I take a plate and if I deform it, it won't plastically deform, it will break, right? Why does it happen, right? So this is really directly related by how these dislocations are formed and how do they move throughout these different types of materials. The other important consequence of this analysis is that if you do have dislocations, you can influence how easily they move throughout the material. So you can, for example, either introduce different types of defects throughout the material to prevent or enhance their movement, and that's the basis of what is called strengthening mechanism. So if you have a metal, you can change its mechanical properties by changing or modifying how these dislocations move throughout the material. So today what we will learn is that dislocations can move, so once they're in the material, they can move throughout the material by two major mechanisms. One is called climb, and the other is called slip. So we will briefly talk about climb, and then we will spend the rest of the lecture today talking about slip. So the climb is a very simple process, but in which dislocation, so this is the first mechanism that we mentioned. So this is the first mechanism by which dislocations can move throughout the material, and it's related to vacancies within the material. So it's a vacancy-assisted type of a dislocation movement. So we learned that for any given material at a finite temperature, there will be a certain number of vacancies, and the dislocations will climb through the assistance of these vacancies. So I will just show you a very trivial climb process. So if you have a dislocation here, so this is this extra plane, this is an edge dislocation that we have. So these will be atoms, right, surrounding it. So there are many of them. So imagine that you have this particular atom here. So this particular atom can jump and take this position here. So this is the first step, the second step would be here. So this light gray atom just jumped. So instead of dislocation ending here, in the second step, it ends up here. And throughout this process, there is a vacancy that is formed in this material here. So this vacancy that can diffuse throughout the material. So the next step 3, again, this is the dislocation. Again, it moved by one step down throughout the material. So this is the vacancy that was formed initially, and it diffuses throughout the material, and eventually it ends up at the surface. Right? So this is the vacancy. So now you can see that instead of having 3 atoms on the surface, there are 2 at the end. So this vacancy that was formed throughout this process just simply replaced this one atom at the surface. So it's a point defect assisted type of a movement of dislocations. So what that means is that you simultaneously have to have point defects and dislocations in the material for this to happen. Okay, so this is the first climb, right? So the second type of how dislocations can move throughout the material is called slip. And this is a very important process, okay? So the question is, if you have a dislocation within the material and if you apply a stress, in which direction this dislocation will move? So the first rule is that, so basically, if you have this extra plane, if you apply a stress in an arbitrary direction, whether this dislocation will even follow the direction of the stress is the first question. The second question, how easily it will move, depending on the orientation of the stress. And the first rule is that dislocation will move in a plane that contains both the line vector and the dislocation, right? So if you have this particular case, the Burgers vector would be here, dislocation line would be here. So for a dislocation to move, the plane in which it moves has to contain both vectors. And you can imagine that there might be, almost infinite types of combinations in crystals in which dislocation can form and consequently move. But in fact, it turns out that the dislocation will be formed and they will move along so-called slip systems. So the slip system in a given crystal, again, the slip system is defined for a given crystal, and it contains two major components. So one is the slip plane and the other is the slip direction. Again, what that means is that if you have a defect in a crystal, the slip system would tell you what is the plane in which dislocation first of all would form and then move throughout the material. And then if you do have that plane, in which direction within the plane it will move. So it turns out that in general cases, the slip plane is the plane with the highest planar densities. And the slip direction will be the highest linear density direction. So what that means is that there are no phones in the room. So what would that mean is that if you have a given crystal, you can easily predict in which plane the dislocations will form, on which plane they will slip, right? And you do this by simply calculating what is the density of the atoms in different planes. So I will just show you an example for an FCC crystal. So if you have an FCC crystal, if you remember from our early on discussions, the highest density plane is which one? For an FCC crystal, which plane will have the highest density? 111, great, okay. So the slip plane will be plane, but we know that there are 4 of them that are equivalent, right? So this is just a group of planes that have a common Miller indices 111. There are 4 of them in FCC. So, and then when you look at this particular plane, then the question is, what are the directions that have the highest linear density? So if this was the FCC 111 plane, there are these 3 directions within this plane that have the highest density. So what are these directions? What is this direction here in the crystal? Hey guys, did you forget about these? What was that? Yes.
Is it 0, 1, 1, 1, 0, 1, and 0, 1, 1?
Correct, yes. It's a combination of 0 and 1, 1, that's right. There are 3 of them. So, what this very simple analysis just showed us is that there are 12 slip systems in FCC crystals. So I can choose any of 111 planes, and I can choose any of 110 directions in that particular plane, and that would be the slip system in an FCC crystal. So what that means is that if you have an FCC crystal, there are 12 equally probable directions or slip systems in which dislocation behavior will happen. So you can do the similar analysis, and you can calculate how these densities look like in different crystals depending on their symmetry. So for example, in the case of copper, there are 12 slip systems. But for example, in the case of sapphire, which is IL-203, there are only 3 of them. So what is the consequence of this? The consequence is that the copper, it's very easy to produce dislocations, and hence this material behaves as the majority of metals. You can deform it very easily. What that means, you can introduce dislocations, and they can move relatively easily throughout the material because there is a wide range of options in which this can happen. In contrast, this particular material and many other materials have a relatively limited amount of, or relatively limited amount of choices in the slip systems, meaning that if you want to plastically deform them and introduce dislocations, it's challenging to do this. And also, once you do form them, dislocations won't move really easily. So again, already this very simple analysis will tell you whether the material is, for example, ductile or brittle. Right, there are many details. We will see that, for example, the strength of the bonding between the atoms also makes a difference or influences this discussion. But already this very simple analysis will tell you whether a particular material will be ductile or brittle.